Hello everyone, we're from Group 5 KPB. We're going to present our report about distribution of solids between two immiscible solvents. So this is all the section that we want to explain in this video.
There are some theories that we use as a basis for this experiment. The first one is liquid miscibility, and the main principle to drive this theory is light dissolve light. As in, substance with similar chemical structure can create homogeneous mixture much easily than those with different chemical structure. Like nonpolar compound tends to dissolve in nonpolar solvent as polar compound with polar solvent. Liquid miscibility also related to distribution law that states if a solid is soluble in two immiscible solvent, then the solute will be distributed between those two solvents, and the ratio of its concentration in each solvent becomes equal to the ratio of its solubility. We then go to some factors that affect solubility of solute inside solvent. The first factor that also has the most impact on compound or substance solubility is polarity. As I stated before, with light dissolve light principle, the similarity of polarity between solute and solvent will impact on how well the solute will dissolve. The second one is stirring, as agitation can help speed up the process of dissolving. While the last one is temperature, where solubility of solute can change depending on the temperature of the solution itself. The next theory that supports this experiment is liquid-liquid extraction that we perform to separate acetic acid water solution and acetic acid ether solution. This method follows the law of distribution, and the result of this extraction is two layers of liquid with different density. The top layer with lower density and the bottom layer with higher density. In this experiment case, aqueous layer that forms at the bottom containing water and solute, and organic layer that forms at the top containing organic solvent and solute. Lastly, there are equilibrium constant, or the value of chemical reaction quotient at chemical equilibrium, a state that a dynamic chemical system approaches after a sufficient time has elapsed, in which its composition has no measurable tendency to further change. The equilibrium constant itself can be obtained through the solid concentration curve in an organic solvent versus an aqueous solvent, with curve equation log concentration of solid in organic equal n log concentration of solid in water plus log n divided by k. The methods or steps that we perform during this experiment are divided into two main parts. That is sodium hydroxide standardization with oxalic acid and determining acetic acid distribution inside two immiscible solvent. In this first part of the experiment, we will standardize sodium hydroxide with oxalic acid. We do this because sodium hydroxide has a hygroscopic nature, so the concentration of sodium hydroxide can change depending on the environment. To standardize the sodium hydroxide, we must first add sodium hydroxide 0.1 normal solution into the bullet as a titrant, while also preparing 10 ml of oxalic acid 0.2 normal solution in an aluminum flask. And with that both out of the way, we can perform the titration with the help of phenolphthalein indicator that works well in the pH of this titration. We then perform the same step 2 more times to get the best result, and we will be able to determine the concentration of standardized sodium hydroxide. In the second part of this experiment, we must first prepare acetic acid solution at various concentration from 0.04 normal to 0.2 normal, and add 15 ml of that acetic acid solution and 15 ml of ether solution into an aluminum flask that we will pour into a separating funnel. With this separating funnel, we then perform liquid-liquid extraction by shuffling the funnel until equilibrium in solution is reached and two layers of liquid are formed. Also, when shuffling, do not forget to open the separating funnel valve regularly, because the mixture has a volatile property, so the vapor needs to be removed into the environment. This is also done so as not to damage the separating funnel that being used. After the extraction is complete, we then proceed by taking the lower layer that contain water and acetic acid from the separating funnel. The last step of this experiment is the titration of acetic acid solution before and after extraction with sodium hydroxide, so we can obtain the concentration of acetic acid, and we will be able to determine the equilibrium constant and dissociation degree of acetic acid.
The third part is data calculation and discussion. The first data that we obtain is environmental data. The first step is to standardize a solution of sodium hydroxide or NaOH with a solution of oxalic acid. Before the titration, it is necessary to prepare a solution of 0.2 normality oxalic acid solution in 100 ml. Oxalic acid has a valence of 2, which is obtained from the ionization reaction of oxalic acid in water, where oxalic acid can release 2H+. So the mass that needs to be weighed is 1.2607 grams, and also we made 0.2 normality NaOH solution in 100 milliliter, so it is necessary to weigh 0.8 grams of NaOH. In the standardization, oxalic acid acts as the primary standard solution because it has a large molecular weight, so it is stable and can be found in high purity. Standardization is done by performing a visual titration, so an indicator is needed as a marker of the endpoint of the titration, namely the phenolphthalein or PP indicator, with a pH range of 8.3 with colorless color to 10 with pink-purple color. Oxalic acid, given the PP indicator, will have no color, meaning that the pH is an acidic state. In addition to the volume of NaOH, there will be a change in the solution to become alkaline until it reaches the equivalent point, which means that all of the oxalic acid has just reacted with NaOH, and 1 ml of excess NaOH indicates the endpoint of the titration with a pink color. The pink color also appears due to the continuous addition of water, so the equilibrium will shift to the right, and it indicates the solution was alkaline. The titration will be carried out 3 times to get more accurate results. From the results of the titration, data on the volume of NaOH used in 3 repetitions was obtained with an average volume of 10.4 milliliter, and through the formula on the screen, the concentration of NaOH is 0.1925 5 normality. Next are the steps to determine the value of acetic acid equilibrium constant between ethyl ether and water that is immiscible, and determine the degree of dissociation of acetic acid in water. The first thing to do is to dilute the 4 normality acetic acid into various concentration in 100 milliliter. For a combination of acetic acid for normality and aqueous can be seen in the following table. Based on the method that have been explained, we need to do acetic acid titration together with NaOH, which has been standardized. Titration will be done visually with the same indicator as oxalic acid before, namely phenolphthalein, where the end point of the titration will be marked by change in color from colorless to pink. That way, the titration results are obtained in the form of NaOH volume of each repetition and the left table. And the average NaOH volume used is 2.3, 5.2, 8.6, 12.3, and 12.7 milliliter. In the table, the volume of NaOH used in titrating acetic acid will increase as the concentration of acetic acid increases, because the amount of acetic acid that must interact with NaOH is also increasing. So the equivalence point will be increasingly far from equilibrium. From the left table, the initial acetic acid concentration can also be obtained in the pink column by the example calculating at the bottom of the table. The next step is to separate with liquid-liquid extraction between water and ethyl ether as a solvent using acetic acid as a solute. The thing that needs to be done is to add acetic acid solution in a separating funnel with 50 ml of ethyl ether and then shuffle it in a roll-up motion until it reaches equilibrium, which is characterized by the formation of 2 layers. Shuffling was done so that the acetic acid can be completely dispersed in each solvent. When 2 layers are formed, the bottom layer will be taken because it consists of acetic acid and water. To find out the concentration of acetic acid after extraction, the layer will be titrated with a 0.1925 normality NaOH solution, and before the titration, PP indicators need to be added to determine the endpoint of the titration. That way, the NaOH volume is used for the acetic acid with 3 repetitions, where the data are listed on the table on the right side. The average NaOH volume for each concentration is 1.8, 3.4, 6.1, 7.1, and 7.5 milliliter. From the calculation results, a concentration of water or acetic acid can be obtained after extraction that lists in the table on the right with the orange column. With the data obtained in the previous slide, the value of equilibrium constant on K and the degree of dissociation or N can be determined. In obtaining values K and N can be used the distribution law, where the regression equation is logarithm of organic concentration equal to dissociation multiple logarithm of water concentration plus logarithm of dissociation divide value of equilibrium constant. Organic concentration can be obtained through the difference from the concentration of acetic acid before extraction and after extraction. The results of organic concentration calculation are attached in the table of this slide. In addition, water has the same value as the concentration of acetic acid after extraction, because the amount of water is described through the amount of acetic acid dissociated with water. Then both data will be logarithmic and plot, with the y-axis is logarithm of organic concentration and x-axis is logarithm of water concentration. From the results of the plot obtained, the regression equation is y equal 1.54x plus 0.32 with the r squared is 0.9138. With this calculation, the value of N or degree of acetic acid dissociation is 1.54, and the value of K or the price of the acetic acid equilibrium between water and ethyl ether is 0.732. From the price of the equilibrium constant or K, which is 0.732, interpreting that the acetic acid has a greater concentration in water compared to the ethyl ether. Based on the results obtained, it is seen that the concentration of acetic acid obtained is getting smaller, or the volume of NaOH used is also less. This is due to the occurrence of an equilibrium between the top layer, or acetic acid and ethyl ether, and the bottom layer, or acetic acid and water, where the acetic acid at its initial concentration will be divided into both layers, so that the acetic acid in the lower layer that has been calculated has a smaller concentration if it's compared to the concentration of acetic acid before extraction. Microscopically, equilibrium will occur dynamically, where the acetic acid will move through the interface between the ethyl ether and water until the acetic acid is completely dispersed in both layers with a constant concentration. Acetic acid have a tendency to have 2 parts that are polar or hydrophilic in the carboxylic part and non-polar or hydrophobic in the hydrocarbon part, so that the acetic acid can be dispersed into both polar or water and non-polar or ethyl ether solvents.
This satisfies the distribution law, which states that when 2 immiscible solvents are added to a solute, the solute will dissolve in both solvents.
In equilibrium, the concentration ratio for each solvent will always remain, but the composition will be different. This is influenced by the bonds formed between each component in each layer. In the acetic acid and water layers, more acetic acid was obtained than the layer of ethyl ether and acetic acid. This is due to the occurrence of dissociation, which forms hydrogen bond between acetic acid and water, where the presence of this hydrogen bond is very strong and increase its solubility.
That's why the amount of acetic acid is more along with water. Hydrogen bonds are very strong because H plus ion, which have lower electronegativity, bond with free electrons from oxygen, which have higher electronegativity.
So, the more free electrons in oxygen will increase the attraction of cations such as H plus to bond with themselves. While in ethyl ether and acetic acid, an association bonds occur, where there is a tendency for acetic acid to form a compound with itself, or it called dimer, because the electronegativity form is greater when acetic acid forms a dimer than acetic acid, which binds to ethyl ether. This is also related to the number of hydrogen bonds formed between the 2 types of bonds formed. Bonds can be compared in picture 1.2, where the acetic acid dimer can form more hydrogen bonds, whereas in picture 1.3, the free electron in the central oxygen ion can only by one ion H+.
The conclusion is the degree of acetic acid dissociation is 1.54 and the equilibrium constant price is 0.732. From these results, it is known that acetic acid has a greater concentration in water than ethyl ether due to the presence of stronger hydrogen bonds. And that's all from Group 5. Thank you for watching.